Okay, so basically this is work that I've done over the past couple of years or so, and it appeared. So it first appeared in a paper with Ruben Monten, who was a postdoc in Saclay and now is at UCLA, and then a bunch of papers by myself. And what this work really is about is studying the symmetries, the infinite symmetries of a certain set of non-local theories which are of interest to holography. That might sound a little bit cryptic, so maybe a more appropriate title for this audience would be on the field theory interpretation of certain asymptotic symmetries. This is really what the talk is about, and so we had some asymptotic symmetries, and we really wanted to understand what they mean in field theory, and as you'll see, it's interesting. Okay, so to start, let me try to explain. So I guess nobody knows what's a non-local CFT, so let me try to introduce these theories, and to do so, actually, could I sit? Is it possible to sit here, or is it too? It's fine. Okay. And to introduce them, it's so there are theories that are a little bit weird from the they're different from the standard framework that we use in quantum field theory. So let me just start by reminding you what the standard local quantum field theory framework that you learn in QFT class is. So if I ask you, for example, to imagine to produce for me some local UV complete QFT, what you'll probably do is imagine there's some sort of conformal field theory in the ultraviolet, and then you deform this CFT by a relevant operator. So this deformation triggers a so-called RG flow. And then somewhere down this RG flow is the QFT of interest, and it's UV complete by construction. So this is what people normally do. The theories that I'll talk about are defined in almost opposite way. So it's very weird from the renormalization group perspective. What we do instead, we start with the conformal field theory in the infrared, and then we add to it an irrelevant deformation. That's generally believed to be, or that's usually an ill-defined procedure for at least two reasons. One reason is that in the case of irrelevant deformations at each order in, say, perturbation theory, there's some ambiguities that appear, and you have to fix them order by order, and they proliferate. So irrelevant deformations are, notoriously difficult to keep track of. That's one problem. The second problem is that even if you define the irrelevant flow in some way, more often than not, these irrelevant flows give you theories that don't make sense in the ultraviolet. They're theories with a cutoff. There's some energy scale between above which they just don't make sense anymore. The theories that I'll talk about are very, very special, in that, first of all, there's some very specific way to fix what the deformation is to all orders in, say, in the deformation parameter. So you have a finite flow in theory space, and there's a very specific trajectory that we know how to define. The second property that they have is that if you take any theory along the flow and you go to the deep UV, there's nothing particularly wrong with it. The theory makes sense up to arbitrarily high energy. The only unusual thing is that its deep UV behavior is not governed by a conformal field theory, unlike these guys. So it's some theory that's UV complete, yet intrinsically non-local in the UV. Okay? And basically, you can get from, if you want, dimensional analysis. The irrelevant deformation comes with a dimension-full coupling. So the scale of the non-locality is related to that dimension-full coupling. Okay? So this is basically a very important, the most important QFT property of these theories. They're not local, yet UV complete. I should say before going on, these two pictures might look similar. So both of them are flows in the space of theories. However, there's a very important difference between them. This thing is an RG flow, meaning the various theories along the flow are related by integrating out degrees of freedom in the previous theory. what I'm doing here is basically an integrable flow. I'm not adding in or subtracting any degrees of freedom. So the theory over here has as many degrees of freedom as the theory over there. It's just a deformation, but there's no RG in any sense. Okay, very good. So, this is these are some properties of these theories. Why would you be interested in them? Well, one reason, of course, it's a QFT reason. These are non-standard QFTs, so you could be interested. And actually, they turn out to be relevant, as argued by these people, to the physics of QCD flux tubes. However, this is not what I'll be interested in my talk today. My interest in these theories comes from the fact that they could provide one way for us to understand holography beyond ADS-CFT. So let me try to just take these flow pictures and translate them into holography. Yes?
When you say non-local, is it non-local in space and time, or only in space?
So I will talk about TT bar, that's non-local in both. And I'll also talk about JT bar, that's local along one null direction and non-local along the other null direction. Yes, but generally they would be non-local on both. Right, so let me try to translate these flow pictures in holographic terms. So over here, this is simple. The ultraviolet CFT translates to some asymptotically anti-de Sitter spacetime, and then the relevant deformation corresponds to deforming the geometries in some particular way as one goes in the interior, and there's some rough correspondence between the radial distance in the bulk and the RG scale in the QFT. So that's something that's very well understood. Oh, I should say, you can interrupt me with as many questions as you want, because I just found out I have half an hour extra. So please don't be shy. Over here, if I try to translate this picture into holographic terms, well, the IR CFT translates to some anti-de Sitter spacetime, and then the irrelevant deformation, if it is single trace, that's a technical term, it corresponds to some non-normalizable deformation of this ADS. So the spacetime becomes non-ADS over here. However, the fact that the theories along this line are UV complete without introducing any new degrees of freedom means that the geometry of here, so I'm not going into full-out string theory in flat space, but there should exist some additional decoupling limit that throws away those modes. But the geometry that I get in this decoupling limit is not going to be anti-de Sitter. It's some non-ADS spacetime, which is dual to this non-local UV complete QFT that lies somewhere along the flow. So that's sort of the holographic picture. And it's interesting because this could be a way in which we, so I should say that, I mean, ADS-CFT is a tremendous success. We have many examples in string theory. We have also a universal approach relating the axiomatic definition of conformal field theories to the emergence of gravity in anti-de Sitter, so we understand it incredibly well. However, holography beyond the ADS is almost unexplored territory. We understand extremely little about it. So the hope is that this could be a way, so this sort of hugely finely tuned irrelevant deformation that produce UV complete QFTs that are non-local could be a way to track down holography for at least the backgrounds that can be obtained from this sort of decoupling limits. So that's sort of the hope. Of course, in practical terms, tracking an infinitely finely tuned RG flow at strong coupling is hopeless. So one has to hope for some special structure. And what's interesting is that if we're in 2 boundary or 3 bulk dimensions, these special structures do seem to pop out. So what am I talking about? So here, I should say I removed all the details from here. So here the context is that we're looking at some backgrounds of string theory, which has this structure. So they have some decoupling limit in the UV. In practical terms, this gives warped ADS 3 spacetime for the experts. So these are basically decoupling limits of black hole-like objects in string theory. So we have these geometries that interpolate between this non-ADS geometry called warped ADS3 to ADS in the UV to ADS3 in the IR. And by the argument I just gave, they're dual to some kind of irrelevant flow like this, driven by what would be a 1,2 operator. Doesn't matter. You know, so it's very hard to track down in field theory what the deformation does. But what we can do, one thing that people do quite often, is try to use some of the gravitational tools, and in particular the asymptotic symmetries, to try to infer some properties of the field theory that's described by this decoupling limit in the UV. So I'm not sure, so maybe Marc didn't get to describing the asymptotic symmetries of ADS3, so that's a highlight of the asymptotic symmetry program. It's a paper from '86, if I'm not wrong, by Brown and Henneaux, where they studied the, so he probably told you that the true symmetries of a gauge theory, and in particular of a gravitational theory, live at the boundary, and it's given by diffeomorphisms that act non-trivially on the boundary of the spacetime. In the case of ADS3, those symmetries famously organize into 2 copies of the Virasoro algebra, which can be seen as a precursor of the ADS3 CFT2 correspondence, because Virasoro is also the hallmark of you know, 2-dimensional conformal symmetries. Okay, so anyway, so we applied this asymptotic symmetry group analysis to this non-ADS spacetime over here, and surprise, we found 2 copies of the Virasoro algebra. And the funny thing is that I explained to you that the dual theory to this thing is not a CFT. It's this non-local UV complete QFT. So what sort of theory is this? Is this some sort of non-local CFT, like some sort of weird theory that has Virasoro symmetries? So Virasoro symmetries are really local conformal transformations. Usually they're implemented like this. You know, what is this? What does this mean? Okay, so the question that this asymptotic symmetry group analysis raises is whether non-local 2-dimensional CFTs, by which I mean UV complete non-local 2D QFTs, defined via a flow like this, with proper Virasoro times Virasoro symmetry, do these theories actually exist? And the answer could be yes or no. If it's no, we go home. If it's yes, then it's really interesting, because there are a lot of things that you can try to understand. First and foremost, how do you reconcile the Virasoro symmetry with the non-locality of the theory? And then you can ask a lot about, you know, consequences on observables, you know, how do you define things, and finally, how do you do non-ADS holography. So in this talk, I will discuss this issue, although we do have quite a bit of progress on correlation functions too. Okay, good. So that's the question. But you know, if you're a hardcore asymptotic symmetry group person, you might say, okay, but sorry, I mean, you know, the asymptotic symmetries in holography, they're supposed to be just the symmetries of the dual field theory. So if you found that the ASG, the asymptotic symmetry group, is Virasoro times Virasoro, that means these theories exist, right? And my point of view is that one has to be a lot more careful than that. And there are a lot of things that one may worry about. the first thing is that the asymptotic symmetry group analysis is usually, it's basically always restricted to just a small part of the classical phase space of the theory. So normally we do asymptotic symmetry group analysis on gravity coupled to a bunch of matter fields, whereas the holographic duality involves an infinite number of fields and strings and God knows what. So we're seeing those symmetries and we're assuming they extend to the full theory. Moreover, in many of the ASG analyses in the literature, many of those analyses are, the gravity theory is truncated to the pure gravity sector. So that raises the question, okay, you might be seeing some symmetries in the pure gravity sector, but do those symmetries survive once you include matter fields? In this paper over here, we actually did include matter fields and still saw the symmetries. So that's another thing. Another sticky point that comes out is that, okay, so in a holographic duality, like for example, we have a holographic pair, the boundary conditions are part of the definitions of the gravity theory. So if I give you some field theory here, suppose that I know what's happening, the gravity theory comes with some specific boundary conditions. But actually, I don't know what they are. So sort of the game that one plays in this asymptotic symmetry group analysis is to come up with try different boundary conditions and see which ones are consistent, which ones give conserved charges that are finite, conserved, integrable, and so on, and try to basically restrict to those boundary conditions that make sense. But you never know whether you've exhausted the consistency conditions, right? So you have this small problem that the boundary conditions are inferred from the consistency of the asymptotic symmetry group analysis rather than being God-given. And then there could be other subtleties and hidden assumptions that we simply don't know about. We certainly make assumptions it's a part of the formalism, so that we also take. I mean, in the case of ADS-CFT, this is extremely well understood, so there's nothing to worry about. But when you try to apply asymptotic symmetry group analysis to some space-time that you don't know the holographic dictionary, you don't really know the boundary conditions, you can ask yourself all these questions. So all this talk was to motivate the fact that it's really important to have an independent definition of the boundary theory and its symmetries, and then use this to check the holographic dictionary and the results of ASG analysis. So you know the boundary theory, you know all of its properties, you also have the bulk theory with the boundary conditions and blah, 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 and then you check that things that you compute over here match the things that you compute over here. You're checking the dictionary. And this is different from most things that people can do normally, because most of the time you don't know what the boundary theory is, so you just use the bulk to try to get something about it. Okay, so what are the claims? I remind you, so I defined the non-local 2D CFT as a UV-complete non-local 2D QFT, which possesses Virasoro times Virasoro symmetry. The field theoretical claim that I have is that some particular theories, which are called TT bar and JT bar deformed CFTs, are actual examples of non-local CFTs. The most difficult part about this, showing this, as I try to explain, is coming up with a well-defined irrelevant flow. But actually, that hard part was done for us by Smirnov and Zamolodchikov, who were able to define these irrelevant deformations and show that they make sense. So that's the hard part. What we did is sort of the easy part, which is to show that these theories actually possess an infinite number of symmetries, which consist of two commuting copies of either Virasoro times Virasoro for TT bar or Virasoro Kac Moody times Virasoro Kac Moody for JT bar. And classically, you can ask classically what these symmetries correspond to, and they basically correspond to field-dependent coordinate transformations. So there's some sort of field-dependent generalization of the, infinite conformal transformations that you have in 2 dimensions. So that's the field theory. On the holography side, it turns out that these theories are holographically dual to ADS3 gravity with mixed boundary conditions for the metric. They basically provide a concrete field theory dual to gravity. So gravity with alternate boundary conditions in ADS3 has been very much studied. But here, sort of, the novelty is that here you have an independent definition of the field theory. You can derive the boundary conditions for the gravity theory. And so you can actually test the asymptotic symmetry group predictions between the 2 sides.
And these boundary conditions are invariant under Virasoro cross Virasoro?
Yes. I mean, the talk is about all the subtleties. Yeah, it's actually subtle. Yeah, but yeah. Okay, so the plan is, so first I'll introduce this Smirnov's homologic of deformations and very few of their properties. Then I'll talk about their holographic interpretation in terms of these mixed boundary conditions. Then I'll switch to field theory and discuss these infinite symmetries of these theories from a field theory perspective. And then I'll make a quick comment on a generalization of TT bar and JT bar. It's the so-called single trace TT bar and JT bar, who are actually dual to non-NDS spacetimes. So they're much more interesting from the point of view of my motivation. And then conclude. Okay, so what are the Smirnov's homologic of deformations? So they're irrelevant deformations of 2-dimensional quantum field theories, which are constructed as bilinears of 2 conserved currents, JA and JB. So what I do is the following. I take this particular antisymmetric combination of the current components. The components are alpha and beta at 2 nearby points, x and y. And what these people showed is that as you take the coincidence limit, you have some operator that appears with a constant coefficient, and everything else is a total derivative term. Okay? So this is basically a quantum definition, a well-defined quantum definition via point splitting of this so-called Smirnov's homologic of operator, which turns out to have some really nice properties that I won't discuss. Okay, so this defines the operator. Now the Smirnov's homologic of deformation consists in adding it to the action. So it's integrated, so the derivative terms don't matter. And so once you add it to the action, so you're in the deformed theory. And then in the deformed theory, you recompute the conserved currents, you reconstruct the Smirnov's homologic of operator, you add that deformed operator to the action, and so on. So you're doing an incremental deformation by the sort of instantaneous Smirnov's homologic of operator. Okay? And amazingly enough, that turns out to be a well-defined irrelevant flow. So you don't have any other counter terms appearing, and you can take this up to finite deformation. So in principle, you can do this with any 2 currents. There are a couple of examples that are universal, and they've been very much studied in the literature. So the first of them is the TT bar deformation, where you take the current components to the currents to correspond to components of the stress tensor, and then you make it Lorentz invariant by antisymmetrizing. And another example is the JT bar deformation, where you take one current to be a U1 current and the other current to correspond to the right moving stress tensor, so the generator of Z bar translations. This deformation breaks Lorentz invariance. However, it has the very nice property that if you start with a CFT, so you see the current has dimension 1 and the anti-holomorphic stress tensor has dimension 2. So this is marginal on the left and irrelevant on the right. So what this deformation does, it actually preserves locality and conformal invariance on the left, while making the theory non-local on the right. So this connects to your question about the non-locality. This guy is fully non-local, but you see that this guy preserves locality in one null direction. And okay, so why is this nice? This is nice, first of all, because this half locality of the theory makes it way simpler to study than TT bar. We really have control over one of the sides and can get stuff. The second reason that this is nice is that this sort of symmetry and locality pattern is precisely what appears in the expected holographic duals to extremal black holes. So this is the thing that connects to the Kerr CFT correspondence. JT bar does not describe a background this warped ADS background is relevant for Kerr CFT, but its symmetries, its quantum field theoretical properties are very similar in this.
Confused by your indices, capital A and B.
Are the labels? It could be 1 and 2.
So
current 1 and current 2.
But downstairs, you don't have a capital A.
Yeah, so here I'm setting A to be the same as the tangent space. You can take them to be 1 and 2, and then you.
No, that's fine. But downstairs with J, there is no second index. So
Exactly. So the first current is just a U1 current. The second current is just.
the epsilon AB.
Yeah, there's no epsilon AB. This thing breaks Lorentz invariance. You don't need the epsilons to.
Can you write it down?
So the deformation is basically JZ T Z bar Z bar minus JZ bar T Z Z bar. Yeah, and there's no Lorentz invariance. Whereas here, because of all this multiplication, you can get it to be Lorentz invariant. Okay, I mean, this is a side comment. This is for the experts. JT bar is really very intimately connected to Kerr CFT and extremal black holes. Why are these deformations interesting? So these deformations have been quite a lot studied in the literature. One of the reasons is that not only can you define this irrelevant flow up to finite parameter, but the theory that you get is highly tractable. So people compute a lot of exact results. They get the exact finite side spectrum of the theory. So that's the spectrum of the theory on a cylinder. The exact S matrix, the theory preserves integrability if it's initially present. So these are all extremely nice properties. And basically from the behavior of the S matrix, the fact that you just know what it is up to arbitrarily high energies, you deduce the fact that the deformed theory is non-local with the scale set by the deformation parameter, mu to some power. But that's actually UV complete because its S matrix actually makes sense to all energies. Okay, so we're precisely in this framework that I was describing at the beginning of the talk. Okay, I don't have time to review any of the many nice properties of these theories, but just tell you something that will be useful later. So as I said, one of the nicest observables to compute in these theories are the finite size spectrum. And how do you get that? Well, so basically you put the theory on a cylinder. So then you just have some quantum mechanical theory with some discrete spectrum. And the point is that the deformation doesn't change the Hilbert space. It only changes the Hamiltonian and its eigenvalues. So you have some flow in that Hilbert space. And the energies and their eigenstates and the energy eigenstates just flow up according to first order quantum mechanical perturbation theory. So I guess everybody should be able to recognize this. Where d mu h is the deforming operator, which is the Smirnov-Zamolodchikov operator that I wrote on the previous slide. And it turns out that many of the special properties so here it's some cartoon of the energy eigenvalues as a function of mu. They're just smoothly deformed. They don't cross. They don't do anything. So many of the very nice properties of this deformation come from the very special structure of the Smirnov-Zamolodchikov operator. So it turns out that this operator can be written as the antisymmetric combination of the zero modes, the spatial zero modes of the two currents, antisymmetrized. plus something that's a total commutator with the Hamiltonian. So it turns out that this guy, so here in the classical limit, you know what this thing is, but okay, more generally, I think it's hard to get it. But the point is that this term doesn't contribute to the flow of the energy eigenstates. You just get the zero mode. And this fact is basically responsible for a very nice property of these theories, is that they have a universal deformed energy spectrum that depends only on the initial spectrum. Okay? So in TT bar, for TT bar deformed CFT, the deformed energies are given by this formula in terms of the undeformed energies and the momenta. For any seed theory, this is the deformed spectrum. You have similar formula for JT bar, where the deformed energy, well, it depends on the undeformed energy, but also the U1 charge, just because this, okay, this guy mixes the U1 charge. But, so this is a very special property of this theory. Another thing I want to introduce on this slide, so okay, this is first order quantum mechanics. I want to define this operator to be chi. So the flow of the energy eigenstates is given by some operator chi that's well defined in the Hilbert space, and its classical limit is roughly that. Okay, so far so good. So I introduced the Smirnov-Zamolodchikov TT bar and JT bar deformed theories. Now let me talk a little bit about their holographic interpretation. So in ADS, yeah.
Before you move to holographic,
yeah.
So this hydrogen growth reminds one of the gravitational theory, which is also non-local in some sense. Will you comment on the relation between gravity?
No, and I'm very confused. So this this talk, I mean, as you well know, you can model TT bar as Nambu-Goto in static gauge, and okay. To me, it's not clear to what extent TT bar is a gravitational theory. Indeed, it has all these gravitational features. It also has a gravitational-like S matrix, which grows like e to the mu, I mu energy, and so on. But I don't know. I don't know what to say. So for example, in the case of single trace TT bar, what you get is that this is supposed to be modeling some two-dimensional compactification of little string theory, which is a theory that does have Hagedorn growth, yet is not a gravitational theory, it's decoupled from gravity. So my own bias would be that maybe it should be some sort of non-local theory, maybe string-like theory, but not gravitational. But
there is no consensus yet on this.
Not to my knowledge, I personally don't see. Maybe if one goes to very high energies, yeah. So one gravitational, quote unquote, gravitational feature that comes from this form of the S matrix is that when you do scattering, you see a minimum length. You might think also that sounds a bit gravitational, but maybe there's a different interpretation. I think it's not very clear. But. Okay, so let me say a couple of words about the holographic interpretation. And the point is that these Smirnov-Zamolodchikov deformations that I introduced in ADS-CFT parlance, they're so-called double trace deformations. Meaning that, well, in ADS-CFT, the operators are matrices, like traces of a matrix, and T is a trace, T bar is another trace, so these guys are double trace. And it is well known that double trace operators, double trace deformations, what they do, they induce mixed boundary conditions for the dual bulk fields. So what do I mean by that? Okay, so if you take the example of a scalar field in ADS, you can do, just solve the asymptotic equations of motion. Z is a radial coordinate, and you find an expansion that, it's a second order differential equation. So there are two solutions which start with these powers of the radial coordinate. And the coefficient of this power for standard ADS CFT with Dirichlet boundary condition is interpreted as the source for the dual operator. I call that source J, which we want to keep fixed if we have Dirichlet boundary conditions. And the coefficient of this power is usually interpreted as the expectation value of the dual CFT operator, and it's supposed to fluctuate. Now, if we take this setup and we add to the CFT action a double trace operator, then actually just in large and field theory, we can do some tricks. It goes by the name of the Happer-Stratonovich trick. And rewrite the deformed partition functions in terms of the undeformed one with some sort of shifted sources. The simplest way to see that is actually by doing a variational principle approach. So, the variation of the deformed action is the variation of the original action minus the variation of this term, and the variation of the original action is VEV times delta source. And then I'm trying in the deformed theory, I'm trying to reinterpret this whole thing as a new VEV times delta of a new source. And by recombining those, I can read this off. So basically, I get that in the deformed theory, the source in the deformed theory is given by the old source, the source in the undeformed one, minus 2 mu times the expectation value, so something like that. Okay, so there's some field theory analysis which tells you how to express the new sources and waves in terms of the old ones, pure field theory. And then to do holography with that, you simply plug in the undeformed holographic dictionary into this relation between the new and the old sources and waves. So in this case, the new source is J minus 2 mu O. So J was phi 0, and O was phi delta. So this is the new source, and since this is a source, I want to keep it fixed. And this gives me the mixed boundary conditions. Okay, so that's totally standard. It's been understood many years ago. And the point is that these TT bar and GT bar deformations can be totally treated in that standard framework. So one basically does a purely field theory analysis that tell us what the new sources and waves are in terms of the old ones. So here, since I'm doing the TT bar operator, so I'm looking at the stress tensor, the source will be the metric, and the wave will be the stress tensor. And we find this nonlinear relation. This is a purely field theory analysis at large N. We can have as many matter sources as we want, and so on. And then we use the holographic dictionary. Okay, what does the so in order to do holography, we need the asymptotic expansion of the metric. In ADS3, it always takes this form. There's some term that goes like 1 over the radial coordinate plus another term that's constant, and then these two terms are universal, and then everything else is non-universal and can depend on the matter fields. And this term is the undeformed source, the undeformed boundary metric, gamma of 0, and this guy turns out to be the undeformed wave. Okay, so we plug this into here, and we find that the TT bar deformation corresponds to some mixed nonlinear boundary conditions for the AD3 metric. We'll keep this combination, which just descends from here with those guys plugged in, fixed. Okay, and then you can plug these guys into here to get the expression for the stress tensor wave. It's some ugly nonlinear expression. Okay, so this is the holographic dictionary. Now you can play with it. So one thing, so of course, when I was discussing the field theory analysis, I always had my TT bar deformed theory on a flat Minkowski background. So what we want to do, we want to set the metric of the deformed theory to be just the Minkowski metric, and then solve for the most general perturbations G0 and G2 that satisfy these boundary conditions. The most general solution in the gravitational sector is parameterized by two arbitrary functions of some, let me call it field-dependent, quote-unquote, field-dependent coordinates, little u and little v. And these guys, these field-dependent coordinates, are determined by the equation that these combinations of them equal the actual null coordinates of the TT bar deformed CFT. Okay, so you see they're explicitly field dependent. And then given this, okay, for L and L bar constants, so we have a background that corresponds to some sort of energy eigenstate, and we can compute the deformed energy spectrum, and it perfectly matches the square root formula I gave a few slides ago. So that's a nice check of the dictionary, and it works very nicely. Another thing that we can do with these mixed boundary conditions is look at the asymptotic symmetries. So we look at the most general diffeomorphisms that preserve this boundary condition, this guy equal to eta. And surprisingly, naively we just expect two U1s, just because the TT bar deformation breaks the conformal symmetries to U1 times U1, but actually find two Virasoros, which are generated by arbitrary functions of this little u and little v defined over here. Okay, I should say so the way, so this is a bit, I mean, it's, no computation is very nice in this theory, so in order to get this result, morally speaking, we didn't quite use the representation theorem. The representation theorem says that the Dirac bracket algebra of the conserved charges equals the Lie bracket algebra of the corresponding diffeomorphisms. In this case, you actually have to use a modified version of the representation theorem because the diffeomorphisms depend very non-trivially on the background fields, L and L bar, so you have to use this modified bracket. But morally speaking, what we didn't quite do that, but morally speaking, we used the representation theorem to get this result. Okay? And this result basically is a first suggestion that TT bar deformed CFTs possess Virasoro symmetry despite being non-local. We can do very similar things for JT bar. So we do this variation principle business. We get some new sources that are shifted by the waves. So when we go in the holographic dual, which is modeled at least by three-dimensional Einstein gravity coupled to U1 Chern-Simons, we need a U1 Chern-Simons in order to model the U1 symmetry that we have in the dual field theory. So basically what we get is ADS3 gravity with mixed boundary conditions that basically mix the Chern-Simons gauge field with the graviton. In the metric sector for the experts, these boundary conditions look very much like Compare-Song-Strominger boundary conditions. But unlike those, because we have this extra U1 Chern-Simons gauge field, we actually can allow full dynamics of the matter fields. So, okay, so we have some boundary conditions that make sense. And again, we can get a perfect match between the energies of the black holes and the deformed CFT spectrum. And then we can do an asymptotic symmetry group analysis. And in that paper, we actually did explicitly use the representation theorem that I just reminded with the modified Lie brackets. And there we get, so if these are the isometries of the solution, so we have an SL2 left. The conformal symmetry on the left. This is U1 left, which is associated to the U1 current. And then we have a right-moving U1, which are the right-moving translations in the non-local direction. So these guys get enhanced to Virasoro Kac Moody, as you expect for local, conformal and affine symmetries. But surprise was that this guy also gets enhanced to a full Virasoro that's generated by functions of, again, a field-dependent coordinate. Okay, so this is what we saw, and we saw this from by using the representation theorem. So, okay, and okay, so this is nice. We can do precision holography despite this deformation being irrelevant. As I tried to emphasize, this is a case in which the boundary conditions for the gravitational theory are derived from the field theory rather than inferred from the HG analysis. So these are. We know that these are the correct boundary conditions, and this has to do with the fact that the bulk and the boundary theory have independent definitions. We managed to keep full dynamics of the matter fields. That's also related, and it's nice. Another comment that's probably obvious. So it's funny. So when you wait, let me just read what I said. So this example shows very explicitly that changing the boundary conditions on the ADH3 metric from Dirichlet, which are the standard boundary conditions which make you be dual to a CFT, to these mixed boundary conditions, which looks like a pretty innocuous change from the gravity side. Actually, this corresponds to a rather radical modification of the dual theory. The theory turns from a local theory into a fully non-local theory. So it's really not innocuous from the field theory side. And then we found these asymptotic symmetries, which are sort of interesting. And the obvious question was, can we reproduce these symmetries from a purely field theoretical analysis?
So the new boundary conditions, you express them in terms of the metric. Can you have a Chern-Simons formulation?
Yeah, Eva Liavres, who was a postdoc at Saclay, she did that analysis, and it's much simpler actually in the Chern-Simons formulation. And I think, yeah, sorry.
And it also relates different powers in the expansion.
It might. I don't know the details very well, but I know she did it, and I think there was some other follow-ups also in the Chern-Simons formulation. So, yeah, so it can definitely be done. Okay, so this is what we found from the, so we're precisely in this case in which we did a gravity analysis. It gives us a very interesting looking result, but we really want to check it. What does it mean from field theory? So let me now turn to discussing the symmetries of TT bar and JT bar deformed CFTs. And actually for the symmetries, so what I'll do, I'll start with a very abstract proof of the existence of Virasoro symmetry in these theories. And the proof goes as follows. So I told you before that if I put my TT bar and JT bar deformed CFT on a cylinder, I don't change the Hilbert space of states, and I get some nice smooth flow. And in particular, the energy eigenstates, which I'm calling n mu, flow with some operator chi, which depends on the deformation, but it's a fully well-defined quantum mechanical operator. That's by assumption, if you want, these theories are well-defined. Now, let me just introduce some operators, which I'm calling L tilde and mu, by the requirement that they satisfy this flow equation. And the initial condition that at mu equal to 0, they just equal the CFT Virasoro generators. Okay, this is just a definition, and it's clearly producing from me some well-defined operator. There's no ambiguity over here, and it's fully quantum mechanical. And I do this not just for the Virasoros. If I have Kac Moodys, I also do it for every extended symmetry. Now, so these are well-defined, unambiguous. These L tildes, they also satisfy the Virasoro algebra by construction. Because if I start flowing the Virasoro algebra, it's a linear flow. And the central charge will be identical to that of the undeformed CFT, just by the flow equation. Okay? Another property that they have is that the eigenvalue of L0 tilde in the deformed theory equals the original. Okay, so if I have some energy eigenstate n mu in the deformed theory, whose L0, which comes from a state n0 in the original CFT, which had the eigenvalue h tilde, the eigenvalue of L0 tilde in the deformed theory in this state will be just h tilde. That's basically a triviality, because this equation implies that this state flows in the same way as just n mu. So they have to be proportional with a mu independent constant, and that's just the original CFT eigenvalue. Okay, so I construct these operators. They have these properties, and but so far I'm just doing just some formal, I don't know if nonsense, but just some formal manipulations. I'm getting a Virasoro algebra, but I haven't shown to you that I have a Virasoro symmetry, because in order to have a symmetry, I need conservation. That's an essential requirement, and this I could do to any set of generators. So now let me actually prove to you that the L tildes defined this way are actually conserved. Just to remind you, the conservation equation is this. So the explicit time derivative of the Schrödinger picture operator moved back to the Heisenberg picture plus the commutator with the Hamiltonian is 0. This is just the d by dt of the Heisenberg picture operator, which has to vanish. So in order to show that this equation is true, we need to compute the commutator of the Hamiltonian, of the deformed Hamiltonian with these L tildes. And my point, so the point is that this h turns out to actually just be a function of L0 tilde and this bar counterpart. How do I know that? Well, I know that, or that fact basically follows from the fact that I have this universal formula for the TT bar deformed spectrum. So remember, when I introduced these theories, I told you that in TT bar deformed CFT, I have a closed form formula given by this for the deformed energies in terms of the undeformed energy and momentum. This is the undeformed energy written in terms of conformal dimension, just to make things more confusing, and this is the momentum squared. Okay, so I have this closed form formula which holds for all the energy eigenstates and actually for any theory, so for any initial spectrum. And now we notice that the deformed energy is nothing but the eigenvalue of the Hamiltonian by definition. And as I just explained, this h tilde is just the eigenvalue of L0 tilde, and the h bar tilde is the eigenvalue of L0 bar tilde. So since this holds for all eigenstates in any theory, this means that I can just uplift this formula to an actual equality between the corresponding operators, which tells me that h is just a function, this particular function of L0 tilde and L0 bar tilde. Once that's given, I can trivially compute the commutator of L tilde m with h, because the commutator of L tilde m with L tilde 0 is just the Virasoro commutator. And what I get here is just I get something that's proportional to L tilde m up to some factor that depends on HMP. So it's an operator valued function whose explicit form is over here. It's totally explicit. But basically the important point is that this commutator ends up being proportional to L tilde m. And yeah, I should have said, of course, these are spacetime symmetries, so we don't expect the corresponding generators to actually commute with the Hamiltonian, but we expect both of these terms to be non-trivial. So now the game is basically to try to add some time dependence to this operator such that this equation is satisfied. And that's trivial. I just do e to the alpha mt L tilde, and these guys are conserved, which means that these generators that I previously showed satisfy the Virasoro algebra are actually correspond to Virasoro symmetries of this theory. Okay, so and this argument is really similar to what one does in standard CFTs. In standard CFTs, the Hamiltonian doesn't commute with the LMs. It's proportional to LM, and you just cook up the time dependence in order to fix the conservation equation. That's the same thing here. The only difference is that whereas in standard CFT, the Hamiltonian is proportional to L0 plus L0 bar, here it's some nonlinear function of it, so you actually get this alpha m which is operator dependent. But that's the only difference.
The very first equation somehow shows that you still have some locality in time, or that it's an ordinary differential equation with respect to time that controls the time dependence. I mean, you don't have an integral over time giving, there is some sort of locality.
This is something that I really don't understand. Yeah, because people usually say that the moment that you have non-locality in time, then your theory is doomed.
Yes.
But it is true that the type of non-locality in this theory must be very special. It's totally not understood, I think.
Since you still have such an equation, which is, I would say, local in time. No?
Right. I mean, I'm constructing my generator so as to, but then they have a very simple time dependence, right?
Mm-hmm.
So, yeah. Okay. Yeah, I have no, there are a lot of very many puzzling issues, just because we know so little about non-local theories, and I don't think I have more intuition than anybody else, but yeah. Okay, so we actually get these Virasoro symmetries, and we actually get 2 Virasoro symmetries. We can play this game for every initial symmetry, and similar results hold for JT bar. So in JT bar also we get some Kac Moody symmetries. But since JT bar is local on the left moving side, what we find is that for the left moving Virasoro in JT bar, this alpha m is actually a number, just like in standard CFTs, whereas for the right moving guy, it's some other alpha m that's operator dependent. Okay, so this is basically the proof that these theories have Virasoro symmetries. It's a bit abstract. So you may wonder, okay, concretely, you know, what do these symmetries correspond to, say, classically? Can I implement them somehow? And it turns out that they're implemented by field-dependent coordinate transformations. So this would be corresponding to the L's and this to the L bars, roughly speaking. So there are translations of the left moving and the right moving coordinate by some function of some field-dependent coordinate, and you also have field-dependent affine U1 transformations in JT bar. And these field-dependent coordinates are universal for each type of deformation in part. So for TT bar, U is the old left coordinate plus some integral of the right moving Hamiltonian, and V is this. And I mean, this looks up to a lot of details and passing between different formalism. This is like the previous expression we had with the L bar and the L in holography. In JT bar, the field-dependent coordinates are actually simpler. So the first one is not field-dependent at all, because this is we have a local symmetry on the left. On the right moving side, the field-dependent coordinate is the right moving coordinate minus lambda times phi, where phi is the bosonization of the ion current. So at least we can write it nicely locally, but it's a field-dependent coordinate. And well, so you can take these generators. So you can show that these charges are conserved by the classical counterpart of the quantum conservation equation I wrote before. And you can compute the symmetry algebra, and you find, depending on the case, 2 commuting copies of the Witt or the Witt-Kac Moody algebra, by which I mean something like this. Q of f with Q of g is Q of this particular function. And this is precisely what you get from these representation theorems in the asymptotic symmetry group analysis. So this matches, and you're very happy. You're very happy, but not for very long, because actually you realize that there's some problem when you try to put a theory when you're trying to put a theory on compact space. So what I was of course, in order to as I said, a lot of the nicest observables to compute in these theories are when you put them on the cylinder, where this is where you have the nice finite size spectrum. So you sort of want to be on the cylinder. You really want to compute, if you want to talk about Fourier modes, you'd better be on the cylinder, and so on. And when you go to the cylinder, I mean, a basic fact of life is that if you want these charges to be conserved, these functions have to be periodic. And, but now you notice that in order for them to be periodic, you need to divide U and V by their respective periodicities, which for these coordinates, for these 3 coordinates, are actually field dependent. So for this guy is, the radius plus 2 mu right moving energy, radius plus 2 mu left moving energy, and this is radius minus lambda times the winding of the field phi. Okay? And given that the algebra was something like this, the radius explicitly pops up in the Witt algebra when written in terms of Fourier modes. And this is really bad. And you have something similar on the right movers, because this field-dependent radius appearing there is inconsistent with momentum quantization. So if you try to semi-classically quantize the theory, the momentum is just Q0 minus Q0 bar in this relation, and you see from here it gets quantized in units of 1 over Ru and 1 over Rv, instead of being quantized in units of 1 over R, the actual radius So this is really bad. These charges are just totally inconsistent at the quantum level. If you look at the particular case of JT bar, where I remind you that the field dependent coordinate is something like this with a phi, you also find an inconsistency of the Poisson bracket with the quantization of the U1 charge, because we also have a U1. And that inconsistency is really easy to track down in this case, of having to do with the fact that the U1 generator doesn't commute with V, and the reason it doesn't commute is because of the zero mode of this field phi that appears here. So if you could somehow get rid of the zero mode that appears in V, you would be able to resolve this problem with the inconsistency with quantization. So, okay, so the solution to this problem is that you can actually, it is actually possible to remove the zero mode while keeping the charge conserved. That's sort of not totally trivial to do in the Hamiltonian formalism, because time and space are treated differently. So you have some, you're subtracting some particular zero mode from here. So you're sending V to some improved little v, such that the corresponding charge is still conserved. And you know, the bar charges, so you get some new charges where you're, the curly Q you're integrating with this F bar of V improved and so on. And similarly for the improved affine guys.
So the improved is the original minus the zero mode or something?
Yeah, minus the zero mode, but the zero mode is pretty complicated. Yeah, it's basically, the zero mode is the generator of spectral flow in the deformed theory, basically.
So that means that it's even more non-local in a sense, or?
Yeah, exactly. It's even more non-local. That's exactly right, because it's a zero mode. It actually corresponds to a spatio-temporal zero mode, because it's also sort of time independent. Okay, so the nice thing is when you do this improvement is that now your Poisson brackets are in principle consistent with both momentum and the U1 charge quantization. You're happy that this in principle can make sense. However, the addition of this zero mode, which as I said is basically the spectral flow generator, so it has non-trivial commutation relations with everything, very much modifies the charge algebra. So before we had Kac Moody, now we're going to get some nonlinear modified mess of that Kac Moody. So it really changes the algebra. However, you can do one more step and take these, these charges that satisfy the ugly algebra, the curly Q bars and J bars. And, okay, you can also take the left ones, which don't do anything. And form these nonlinear combinations of them. This nonlinear combination basically looks like spectral flow by lambda times the right-moving Hamiltonian, roughly speaking. And when you take this particular combination of those, you find that the resulting guys, which I'm going to call L tilde, do satisfy a nice two commuting copies of Kac Moody. And actually, they satisfy the flow equation with respect to the classical limit of that operator chi. What this means is basically that if I want to know what's the classical realization of the Virasoro Kac Moody symmetries that I was finding in the quantum theory that I defined abstractly quantum mechanically, which are basically these L tildes and these J tildes, well, they're related to the standard generator, the field-dependent generators defined like this. The ones with the zero mode removed, because otherwise they wouldn't even make sense. They're related in this nonlinear way. So yes, we can reproduce the symmetries, but it's complicated. And I should say, okay, so this is published. We're currently working on the TT bar case, which seems to, I mean, it works in a similar manner. We again have to remove some particular zero mode, and we get a non-trivial relationship between the naturally defined charges and the Virasoro charges.
And how did you arrive at this combination?
By studying the flow equation.
So the nonlinear modification of Kac Moody contains lambda, and you deform in
yeah, so you can compute it in two ways. You either take your V improved over here and just compute Poisson brackets, or you use this. These guys just satisfy Virasoro Kac Moody. So it's simple. So you just invert these relations and find the nonlinear modification. OK, so what lessons do we draw from here? So as suggested by the asymptotic symmetry group analysis, we find that the field theory analysis does indeed reveal the existence of two Virasoro or Virasoro Kac Moody symmetries. But these symmetries, in the classical limit, where we want to realize them specifically, they bear somewhat complicated relations to the generators of field-dependent coordinate transformation. We have to remove the zero mode and do nonlinear combinations and so on. In addition, these symmetries are different from those predicted by the asymptotic symmetry group analysis, which are the guys that I talked about here, these guys that are actually inconsistent in finite size. They're the guys who have this algebra that was inconsistent. So from this I get, OK, so the HG at the end, it gave us a really interesting hint that there's something very interesting happening in this theory. But actually, it didn't give us, or at least the naive analysis that we did, based on these representation theorems, like we didn't go in depth and try to see whatever. It didn't really give us the actual symmetries of the theory, which are the guys with the zero mode removed.
Okay, so it's different because the zero mode is not removed on the gravitational side.
Yeah, so basically, this removal of the zero mode is something that we
Sigma is not periodic on the gravitational side? Or?
Yeah, it is periodic. So the problem is that we only understand this business with the zero mode and the well-defined symmetries in Hamiltonian language, whereas the gravity analysis is a Lagrangian analysis. And the problem is we really don't understand the symmetries in Lagrangian language in field theory. They look very strange. They look like some sort of field-dependent symmetries, but then accompanied by some sort of very large affine transformation or maybe some very large rescaling, and we haven't been able to make sense of them yet in Lagrangian language. So I think that's part of the problem.
Could you do the Hamiltonian gravitational analysis?
I feel that one has to be very hardcore to do it, but but yeah, that would be a different option to. I mean, we're trying to go the Lagrangian way because it's anyways nice to understand these things in Lagrangian formalism. But yeah, that would be a different thing. But you know, this naive analysis, I'm not super naive, but this matter of fact analysis that we did that does not produce the actual symmetries with the zero mode removed. So how to reproduce them? So one way would be to try to understand already in field theory the symmetries in Lagrangian language, which is closer to what we did on the gravity side. Another thing would be indeed to try to do the Hamiltonian formulation in gravity. That's another possibility. Another thing would be to try to go and look for subtleties that we might have missed in the HG analysis. Maybe there's something very special happening with the zero modes. We didn't expect any big subtleties, so maybe if we look for them, something will happen. And another maybe also valid question is whether the standard assumptions of ASG analysis are satisfied. As I said, we have to remove the spatio-temporal zero mode. That's a very non-local procedure. I've never seen something like that done in gravity before. Maybe there's some new rules. I mean, hopefully I'm just saying nonsense here, but this is to say that I really don't know what's happening and what's the resolution of this tension. And sort of the final lesson that I wanted to rehearse is that having an independent definition of the field theory and its symmetries was basically essential or will be essential in properly understanding the asymptotic symmetry group. OK, I could end here, but let me just have one slide on the implication for non-ADS holography, because my whole motivation was based on understanding non-ADS holography, and these things were just ADS3. And that has to do with these single trace analogs of the TT bar and JT bar deformations that were introduced by Kutasov and collaborators. So these deformations, unlike the double trace TT bar and JT bar, which are totally universal, you can do them on any CFT, these guys are defined in a string theory setup, more precisely by looking at the field theory that emerges in the near horizon of the NS5 F1 system, which is basically a symmetric product orbifold CFT, where P is the number of F1 branes. So because you have the symmetric product orbifold structure, you can do a single trace analog of TT bar, where you just sum TT bar over copies, rather than, as opposed to the double trace, where you sum Ti times sum T bar J. This is a single sum, so this is single trace. And because it's single trace, this actually corresponds to a non-normalizable deformation of the geometry, which will end up interpolating between ADS3 and the IR, the ADS3 dual to the CFT2, and some spacetime that's asymptotically flat with a linear dilaton in the UV. So that's a really nice, interesting spacetime. So their proposal is that this thing is dual to the symmetric product orbifold of TT bar deformed CFTs. And as far as I know, this is one of the few concrete holographic duals proposed for non-ADS spacetimes. You can do the same thing for JT bar. So you take the same setup, but you deform by single trace JT bar over here. What you get over here is a warped ADS3 spacetime. And this is supposed to be a concrete string theory proposal for holographic dual to warped ADS, which it's nicely connected to Kerr CFT, extremal black holes, and so on. Now, what's the point? The point is that one can do a field theory analysis of the symmetries of symmetric product orbifolds of TT bar and JT bar deformed CFTs, and show that these Virasoro symmetries actually survive the orbifold. So they survive, and they're as complicated as they were before. So that's nice. So if they survive it, a natural question is, can the asymptotic symmetry group analysis in this sort of background actually capture them? Well, I don't know what the answer is. This okay, this we've already shown. This is work in progress. But if it does, it would be really interesting to carefully understand the dictionary and the interplay between symmetries and the field theory, which is a bit complicated, that I try to show, and so on. And maybe eventually understand the full holographic dictionary, and then maybe generalize it to other non-asymptotically ADS backgrounds. Okay, so with that, I'll end. Thank you.